Hello everyone, welcome to our talk Static Partitioning Virtualization on RISC-V. In a nutshell, in this work we have implemented the RISC-V Hypervisor Extension in a Rocket car, and we have run our open source static partitioning hypervisor Bao on this car in an FPGA platform. My name is Sandro Pinto. I'm a research scientist and assistant professor at the University of Minho, where I currently lead the embedded system research group. I'm also actively involved with a RISC-V security startup from the Bay Area. With me today, I have José Martins, which is a very talented person, and he is currently pursuing his PhD on trustworthy real-time virtualization under my supervision. So this is the agenda for today. I will focus on the first 2 points, and then José will go through the implementation and evaluation of the RISC-V Hypervisor Extension. At the end, I will briefly discuss some final thoughts and takeaway points. So a brief contextualization on the topic. Well, in domains such as the automotive and industrial automation, the number of functional requirements has been exponentially increasing over the past few years. For example, in the automotive industry, there is an ongoing trend towards fully autonomous connected cars, which presents a huge challenge in terms of complexity to the need of consolidating multiple heterogeneous software stacks with different criticality levels. For example, the network connecting infotainment system is typically deployed alongside the safety-critical airbag and braking systems. At the same time, the market pressure to minimize the swap-C, size, weight, power, and cost is pushing for the consolidation of several subsystems in the same hardware platform. Well, virtualization, an already well-established technology in desktops and servers, is a natural enabler for mixed criticality systems for consolidation and integration. It requires minimal engineering efforts to support legacy software while guaranteeing separation and fault containment between virtual machines. The mission-critical nature of mixed criticality systems also requires close to native performance, real-time guarantees, and strong security, with those last two metrics being the ones typically not addressed out of the box in existing hypervisor solutions. Traditional hypervisors, for example, KVM and Xen, were not designed to address the strict requirements of mixed criticality systems. There are some works reported in the literature that have achieved some degree of success, but generally speaking, none is an optional solution because they tend first to have high overhead in terms of I/O due to the use of techniques such as emulation and paravirtualization, and a large trust in computing base due to the implementation of hosted architectures in the case of KVM, or due to the dependency on privileged virtual machines or large monolithic operating systems. Static virtualization, quite established in the open source community with JLAWs, can be seen as a thin configuration layer that partitions at design time all system resources, one-to-one mapping between virtual and physical CPUs, static memory assignment to each virtual machine, device pass-through policy, and so on. Although JLAWs is getting traction and used both from academia and industry, JLAWs has some bottlenecks regarding its applicability for mixed criticality use case. For example, JLAWs depend on a Linux root cell, which enlarges significantly the attack surface and the TCP of the system, and the boot time is also large. The Xen project also has identified the opportunity of mixed criticality applications in the market, and that's why they have recently released the Xen DOM Zero-less, which simplifies the Xen architecture to not depend on DOM Zero. Well, back to the end of 2018, we start looking at the existing open source hypervisors, and if we felt that there was an optimal solution to address the strict requirements of mixed criticality system. That's why we have decided to implement Bao. Bao is a type 1 bare metal hypervisor which implements the static partitioning architecture. Bao has no dependencies on external libraries or privileged virtual machines and relies mainly on hardware assistance for many of its functions. That's why the key aspect of Bao comparing to other existing open source solutions is the size of the TCP. It's approximately 7K software lines of code and is going down. Bao also implements from the ground up a set of mechanisms such as the cache coloring that aims at reducing freedom from interference between virtual machines and preventing microarchitectural side channels. If you want to read the technical paper from Bao, you can refer to this link. Well, Bao has currently support for the latest RISC-V Hypervisors extension specification, and we are running Bao both in Chemo and also on the Rocket chip that we have extended with the virtualization support. Bao is also fully integrated with the OpenSBI, and we have demos with different configurations of the virtual machines like bare metal applications, FreeRTOS, and also Linux. Well, a quick overview on RISC-V virtualization. The Hypervisor extension is part of the privileged architecture of the RISC-V ISA. The H-Extension is designed to support the efficient hosting of operating systems atop both Type 1 and Type 2 hypervisors. In terms of execution modes, the supervisor mode is extended to Hypervisor Extended Supervisor, and there are the Virtual Supervisor, VS, and the Virtual User, VU. There are additional CSR registers to manage hypervisor capabilities and for accessing guest state. And of course, there is also a two-stage MMU responsible for translating guest virtual to guest physical address in stage 1 and guest physical to host physical address in stage 2. Well, to get that in, this clearly visualize the privilege levels. At the bottom layer, which means at the higher level of privilege, we have machine mode, intended to host the supervisor binary interface. Atop the machine mode, instead of the S mode, we have the HS mode, intended to host the hypervisor. And atop the hypervisor, we have the VS and the VU that are intended to host the guest OS and the guest OS applications in a virtualized environment. And to speak a little bit about the spec is currently in version 0.6.1 and have significantly evolved with great feedback from open source projects and from contributions both from organizations and individuals. The spec is close to free state. There are bi-weekly calls to discuss virtualization related topics, so feel free to join. As of now, the H-Extension has achieved function completeness with KVM and Hypervisor, but to freeze the specs, there is the need for more RTL implementations and to get other hypervisors to run on those implementations. Just to conclude this part, the H-Extension has been evolving mainly with support from two open source hypervisors, KVM and Hypervisor. KVM is representative of a Type 2 hypervisor, and Hypervisor from ANOP is representative of a Type 1 hypervisor. We have also ported Bao to RISC-V as representative of the static partitioning architecture, and we are definitely engaging with the RISC-V community. I will now hand it over to José, which will describe the implementation and the evaluation of the H-Extension in a real RISC-V core.
So now I'll talk a little bit about our implementation of the hypervisor extensions on the Rocket chip and about some enhancements we added to the system in order to minimize interrupt latency and interference between virtual machines. So as Sandro said before, our implementation in Rocket chip is according to the latest 0.6.1 version of the specification, but we only support 64-bit guest and hypervisors and the 41-bit guest physical address space second stage translation. So we've implemented most of the spec, practically all of the spec, but we haven't implemented either VMID support nor transformed instruction pseudo instruction exception information. But both of these features are optional, so we can say that our implementation is following the spec. So our implementation is open, is available in this GitHub repo. Please check it out. And it's synced up with a version of Rocket chip from about 6 months ago. So it took us about 1,100 source lines of code to implement it using Chisel, of course. And we're mainly focused on the CSR module, which implements all the privilege level logic. And we extended the page table walker and the TLB, of course, to implement the second stage translation. So right now we are currently working in refactoring the implementation because we feel that we can really improve and optimize and minimize what we did until now. So we plan to add some of the missing features and also optimize the second stage translation by adding specific data structures for just for the second stage, such as TLBs and wall caches. Regarding the software we have run in our implementation, we started by running only bare metal ad hoc testing to verify the behavior of specific features of the extensions. Then we started running our own Bao hypervisor, and finally we have run the Hypervisor hypervisor. So we have mainly been running this on an FPGA. So in static partitioning virtualization, you typically want to directly assign devices and their interrupts to virtual machines. However, without interrupt virtualization support, the hypervisor itself must receive the interrupts and then inject it on the virtual machine. So this really increases interrupt latency. Furthermore, the interrupt controller must be fully trapped and emulated by the hypervisor. So to take advantage of the feature of guest external interrupts of the RISC-V Hypervisor extensions, which allows an external interrupt, physical interrupt, to be directly injected in a running virtual machine, we have extended the PLIC, the RISC-V standard interrupt controller, to take advantage of this feature. So our main requirements is just to have extended PLIC as minimal as possible, so to allow this direct injection of physical interrupts with no traps on the claim incomplete registers, and allow a mix of physical and virtual interrupts, so that a given virtual machine can be assigned a physical real device and also have a different device emulated by the hypervisor. So to do this, we just added extra context to the PLIC, which are essentially these lines from the PLIC to a given privilege level in one of the RISC-V hearts. We just added more context for the virtual supervisor mode. And the hypervisor must still trap and emulate the access to the VX context priority enabled registers. But the access to these registers, to these configuration registers, is not really critical to interrupt handling. And the hypervisor directly maps the claim and complete registers so that the physical interrupt can be completely handled by a guest without hypervisor intervention. So to allow virtual interrupts, we extended the PLIC memory map with these virtual interrupt injection registers. For those of you which are familiar with ARM's GIG, they are similar to the list registers, but we did this in a different way, which centralizes interrupt management for a given virtual machine. So if you want to know more about this extension, please check out this GitHub repo, with a small caveat that the PLIC itself might be deprecated in the near future and replaced by a new standard interrupt controller. So, but we still hope that these ideas are useful in the new incarnation of the PLIC. So also one of the main goals of static partitioning is to guarantee this freedom from interference among the virtual machines to ensure some real-time properties. So typically, this type of hypervisors implement some type of software-based mechanisms to partition memory system resources. For example, page or cache coloring to partition the last level cache. But typically, these techniques increase the complexity of the software and have high overheads. So we want to take the advantage of having this open and moldable hardware to try out lightweight hardware mechanisms to accomplish the same goals. So we started by slightly modifying the L2 cache with a per bus master way locking mechanism, and then we added this rocket chip model called the Bandwidth Regulation Unit, or BRU, developed by researchers at the University of Kansas and University of Berkeley, that allow us to group RISC-V cores, RISC-V hearts in domains, which in our case will be virtual machines, and limit their maximum bandwidth. That is, limit the maximum number of memory access in a given period of time. So now I'll show a small evaluation of the RISC-V extensions we have implemented. So we did this using FireSim in an hexacore rocket configuration with all the add-ons I talked about in the previous slides. So we ran the benchmarks in bare metal applications and Linux OS applications, which run on top of our Bao Hypervisor, which itself runs on top of OpenSBI. We look at two metrics, performance overhead and interrupt latency, in 5 system configurations. So bare metal execution, where there is no hypervisor. Then we look at single guest execution to assess isolated effects of virtualization. In the third place, in the cores that are not executing the benchmark, we run a virtual machine that has several interference applications, which are essentially continuously writing to a large array of memory that's larger than the L2 cache. And finally, we enable the memory resource partitioning mechanisms I discussed in the previous slide to understand its effects on the solo execution of the benchmark and its efficacy in minimizing interference. So basically, we assign half of the cache space to each of the partitions and half of the total measured bandwidth to each of the partitions. So analyzing the performance overhead, we use the MyBench benchmark suite, the automotive subsets. The results you will see here are relative to the bare execution case, so higher values are worse. First, we see that there's a non-negligible overhead up to 6% due to virtualization itself. So we believe that this number should be somewhat smaller, and we believe it's mainly due to two reasons. First, because there's a high cost of timer management, which is done via SPI calls and incurs in two traps, one to the hypervisor, then one to the OpenSBI to the firmware, and injecting the timer interrupts incurs also in these two privilege level changes. The second reason is because there's a lack of optimization in second stage translation, as I mentioned earlier. Then we have the interference applications, and we see it has a nice impact in the performance of this benchmark. In one of the cases, it goes as high as 70%. Finally, we enable the memory resource partitioning. When we enable the memory resource partitioning, you can see that we can significantly reduce the interference with only a small cost to the performance under no interference. So finally, we look at the interrupt latency. To measure it, we use a custom benchmark, which consists in a bare metal application that programs the timer to interrupt it periodically, and then it measures the delay between the time the timer triggered and when it started handling the interrupt. At each measurement, we also invalidate the L1 instruction cache, as we believe it is more realistic to assume that this cache is not hot with respect to the interrupt handling code. So here we see the interrupt latency for bare metal execution. We see that it's quite low, about 199 nanoseconds, and this is really steady. Then we look at the interference when there is full trap and emulate and the hypervisor is re-injecting the interrupts in the virtual machines. We see that there's a significant increase in latency and that it's very susceptible to the effects of interference. And finally, we enable the mechanisms that allow direct injection in the virtual machine, and we see that we achieve near native latency with little susceptibility to the effects of interference. So now I will pass it back to Sandro to finish the presentation with some conclusions.
Thank you, Jose. So final thoughts and some takeaway points. Well, we are in a position to say that we have presented the first public implementation and evaluation of the hypervisor extensions in a real RISC-V core. And taking into account that as of today, there are no real commercial silicon which implement the H-Extension, and probably it will take some cycles till we reach there, we start thinking how we could leverage the existing Linux-capable RISC-V cores with M, S, and U mode to implement static partitioning virtualization. And we effectively can do that. And we have a work in progress porting of Bao to the PolarFire Icicle SoC that we are start to test in Renault. This basically enables consolidation and isolation for mixed criticality systems using RISC-V as of today. So final takeaway points. We have provided a clear picture about the state of the RISC-V hypervisor extension, and we strongly encourage all of you to participate and to contribute. We have provided the first implementation of the H-Extension in a RISC-V core, but to get the spec to free state, we need additional implementations from other folks. And finally, last but not least, we have introduced the static partition virtualization, and the hardware needs to do it efficiently. And we have identified some gaps in RISC-V that must be addressed sooner rather than later. For example, ARM has recently specified the MPAM for the memory system resource partitioning, and there are no standard extensions at this level in RISC-V. Well, I thank you for your time. I hope you have enjoyed the presentation, and here you can find our contact, so please do not hesitate to reach out if you have any doubt, question, or suggestion. And we are open now to address all your questions. Thank you once again.